Record is on. So I have an example here that I want to look at. We're going to start off with a $50,000 investment or $50,000 amount. And what I want to compare here is an annual growth rate of 5% versus a slope of just $2,500 a year. So this could be thought about in a lot of different ways. Like maybe you just came across $50,000 and you want to invest it for the future. And one company says, hey, we'll give you 5% per year. Another company says, we'll give you guaranteed $2,500 a year, right, into your account if you let that $50,000 sit there. So we just want to compare what these two look like. And I'll do a little by hand and then we'll do it in the spreadsheet. So when we work with exponential functions, we're given what's called a growth rate here. So that's my R, growth rate. And what I immediately want to do with R is I want to turn it into what's called a growth multiplier. Growth multiplier. And we've been doing this since the beginning of this week. And the growth multiplier is where you add 1 to that growth rate. So I take my 5% as a decimal and I add it to 1. Oops. There's my 5% as a decimal. And then I get 1.05, which, just a reminder, if I were to turn this back into a percent, that would be 105%. Okay? And this number right here is known as a growth multiplier because I can just multiply by my principal to get the new amount. So we have our formula, recall, that says the future amount is equal to P, parentheses, 1 plus R if it's annual compounding, to the power T, where T is the years. And again, what I'm saying here is that this parentheses 1 plus R is what I refer to as a growth multiplier because we simply multiply it to get the future amount. So for this situation here, my formula would be $50,000 times 1.05. Since I did the addition, I don't really need the parentheses. If the addition was still there, I would need the parentheses. And then I just raise that to the power T. So we'll calculate that for some various values of T in just a minute. But I want to look at the linear side. On the linear side, I'm just adding this amount each month. When I do repeated addition, that turns into a multiplier. So the model here, let's use, it'll stick with red, is going to be a y equals mx plus b type thing. And my m is this dollars per year, right? That's my rate of change here, my slope. So we still need to know about rates of change and slope from the last unit. They're still going to come up here and there, but now we have this slightly different way of looking at things. And sometimes things line up and sometimes they don't. Just kind of depends. So in this case, I would get y is equal to the 2,500. X is my years in this case, plus the starting amount, which is my $50,000. So just a reminder about what these numbers mean. So this one is my initial value, my starting amount. Sometimes it's called the y-intercept, right? And this one right here is my slope, okay? Now, both models need a starting amount. With the exponential models, the starting amount is a multiple. With the linear models, the starting is a addition. So I'm just going to whip out a calculator and look at a couple of keys for this. So bring my calculator in here. And let's get 2 screens on that. And another version. So let's just go 2 + 2 for a new calculator. Split this over here. So I'm just going to get 2 calculators going to see what's happening. So this one right here, in the left will be the exponential one. So I had 50,000 to start with. So let's look at 1 year later at first. So then I would go times the 1.05 raised to the power 1. Now, raising something to the power 1 doesn't change it, but I'm going to put it in there anyway because I'm emphasizing this is the first year later. So 1 year later, I would get that much. Now, it turns out 5% of $50,000 is 2,500, so that's going to match the linear one. So I'll do the linear one on this side. So 50,000 plus, right, the linear, we add on the initial amount, and then we get 2,500 per year, so I would go times 1 for 1 year. Okay? So the first year after they match, but then later they're going to be different. So let me add that to my notes. New page. Oh, Zoom, you are in the way. Why don't you move down here? New page. All right, so we've got the A equals 50,000 times 1.5, oops, 1.05 to the T versus Y equals 2,500 X plus the 50,000. And we found that in 1 year, they would match. 1 year later, this would be 50,000, 52,000, sorry, 500. And this one would also be 52,500. And they're the same because 5% of 50,000 is that 2,500, 2,500. So let's look at 5 years later, what's this gonna look like? So we've got our calculator here. So then we just use the same formula, 50, 1, 2, 3 times 1.05. This time I want to raise it to the power 5. So 5 years later, I've got 63,814. And on this one, it would be the 2,500 times 5 years later plus the initial amount, $50,000. And so that one's 62,500. So they're a little bit different. So I'm going to put this over here so I can see it. All right, so 5 years later, this one right here is 63,814 and 8 cents rounded. And this one right here is 62,500 because we're only getting 2,500 a year. But here we're getting 5% of whatever we had before, and whatever we had before is bigger than what we started with, so this one is going to grow faster. Notice how much bigger this one is than that one already. And over time, what we're going to see is that that's going to keep happening. So I'm going to show this in a spreadsheet next, and then we'll take a look at a similar kind of problem. So somewhere I've got a spreadsheet. All right, here we go. So I already set this spreadsheet up. And notice I did one like this yesterday in class. I'll show how I made these calculations in a sec, but I just want to take a look. So I started with the 50,000, so they're both gonna initially have the same amount. And so this could be, say, a starting salary, and one company says they'll give you 5% extra per year for a raise. The other company says we'll give you 2,500 per year for your raise, right, guaranteed. And if we look at linear versus exponential, I've got them in reverse order here than I had them in the notebook. This is my linear column. It's always going up by 2,500. My exponential column is compounding that interest, okay? And so it's exceeding after the first year, the linear one all the time. So let's look at a graph of these. I'm just gonna add a few more years on just so we can see what linear versus exponential looks like for 20 years. So graph, data, and insert charts. And what kind of chart will it give me? A line chart, nice, okay, that works. Okay, so here, the blue one is my linear. That's just this straight line of points I got going on. And the exponential, because the interest is compounding, my raise is compounding itself, I end up with a much better deal over time. So this exponential one has a curve to it. If it didn't have a curve, it would kind of match up with this one, but it's kind of hard to see, but there is a slight curve going on with this one. The farther I look into the future, the more obvious the curve is. So it just kind of depends. 5% isn't all that big, so the curve is very subtle, but this is curving upward. All right, let's get rid of that. And then I'm going to demonstrate how I did this with a different set of numbers. So let's suppose right away, you know, you're looking for a job and one company says they'll all start at 50,000. One company says 5%, but you like the other company, but you don't like that raise. So they say, fine, okay, well, if we really want you, we'll give you a better raise. So let's say they're going to up it to $3,000 per year every year for your raise, which means it's a better deal after a year or two than the exponential one. So I'm just going to delete this stuff and start over. So the way I would do this on a spreadsheet, because I can see a whole bunch of years at once, it's kind of nice. I'm just going to use the information above. So the information above for linear says use your slope times your x value, which is the years, and then add on your initial amount of pay, which would be the 50,000. So that's my y-intercept for the linear. Okay. Now, when I fill this down, I want the years to increase. That's good. But my starting salary is always 50,000 and I'm only getting $3,000 per year. So I got to tell the computer that these will change, but these two numbers will not. And the way you do that is the things that don't change get a dollar sign. So I'm always getting $3,000 a year. So I'm going to put a dollar sign in front of the 3 for B3. And my starting pay is what it is. So that's always in row 1 there. So I put a dollar sign in front of the 1. So if things are fixed in a spreadsheet, like the starting amount or the slope, they get a dollar sign. If they're changing, like the years, they don't get a dollar sign. And again, I'll keep demonstrating that as we go on. Similar for exponential, this one, we start with the initial pay, and then we multiply by parentheses 1 plus the rate. And then we raise with the little hat button to the number of years. In this case, the years change, so no dollar sign, but the other two figures need a dollar sign to fix the row. Otherwise, the computer will get all screwed up. And I'll do a spreadsheet like this at the end of class too. Once I have that formula set, if I have all the dollar signs in the right spot, I can just fill it down. So we can do a comparison over time with these two. So what we can see is at first, the linear has a bigger raise, 3,000 versus 2,500. And it continues to be a better deal than the exponential for a while. But then all of a sudden, the exponential starts to catch up. And then finally, not in the 8th year, in the 9th year, that 5% raise compounded starts to be a better deal. And it's going to be a better deal forever after because the exponential one curves upward. So let's look at a graph of that to see where they start and separate, meet again and separate again. This is kind of cool. Okay. And if we zoom in on this part here, you can see the blue line's a little above. Let's see if I can get that zoomed in to own sheets. And you can kind of see it in there. The blue's a little above here. The linear one is a better deal for a little while, but then all of a sudden the red one catches up and exceeds it, okay? Because the linear one's always straight, the exponential is curving upward. So even though the linear starts off a little better, I wonder if I narrow this, if we can see that better. Let's pull that out, have it. It's still kind of hard to see. That's all right. Let's put that back here. All right, so what's the point here? The point is if something is exponential, it curves. If something's linear, it's straight. And exponential functions, if it's increasing, will always eventually outdo a linear one, is the moral of that story there. Okay, and there are a couple of homework problems related to a comparison between linear and exponential that you're gonna have to do. All right, back to the notes. Next. All right, we just did that one. Okay, so the next thing I want to do is I just want to emphasize the importance of growth rates and growth multipliers. So in the formula that we're using, we have two versions of the compound interest formula, but the easy one is just the 1 plus the rate. So I'm just going to stick with that. Now, it turns out that there's many situations that have rates of change that are percentages. Sometimes it's an increase, but sometimes it's a decrease. So I just want to go over a few examples. So we just looked at one that was an increase. And so to turn that growth rate into a growth multiplier, all we do is go 1 plus as a decimal. And so my growth rate, my growth multiplier, is the important part, is 1.05. And that's what goes in my formula. It could be instead I have a decrease. Like a few years ago, I saved up a bunch of money and I bought a new car. I got a Subaru Outback and it's awesome. However, every year it's worth less than it was before. So let's say that my car every year is worth 15% less than it was the year before. Okay, so that would be a decreasing rate. So it's a negative rate because I'm losing money on my car. The multiplier for that one is kind of like the one above, but I have a minus. So that would be 1 minus 15% as a decimal. And so that was going to give me, I think I'd end up with, if I lose 15%, I keep 85%. So 0.85 is my multiplier in the formula. So for example, if I extend that to talk about my car for real, new page, my new car, it's shocking how much cars are in trucks, was $35,000. And it's loses 15% of its value per year. Okay, so the loses 15% means R is negative 15%. For my formula, it's the same formula I've been using, A equals P times 1 plus R to the T, right? The parentheses is my growth multiplier. So now I would get $35,000 times 1 minus 15% as a decimal to the power T. And we can clean up what's inside the parentheses. We can take 1 minus 0.15 and say that's really 85%. Since I did the calculation, I don't have to have the parentheses. So I could simply write this as 35,000 times 0.85, 85 hundredths to the power T. So this is the formula that tells me what my car is worth. So if my wife says, hey, what's it going to be worth 5 years later? We've had it for like 3 years now, and 2 more years, 5 years will have passed. So I can just plug that into my calculator and see. Oops, where'd it go? Calculator, where are you? Oh, I moved it to the other screen. Gotcha. So if I take my 35,000 and I multiply by that, it keeps 85% of its value because it lost 15%, and I raise that to the power 5. So 5 years after I bought it, it's now only worth like 15,500. Holy crap, it used to be worth 35,000. Oh my gosh, where'd all my money go? Hopefully I got a lot of good times out of that car in that time. But now, at 5 years later, it's only worth $15,500. Okay, so if I wanted to resell it, my $35,000 car from 3 years ago, 5 years later, is only going to be worth $15,500. Now, some cars keep their value better than others. So it could be some vehicles only lose like 5 or 10% per year, while others might lose 30. All right, so let's look at another percent change. So a percent change could go up. Growth multiplier is 1 plus something. Could go down, so we have 1 minus that percent change, and we end up with this base that is less than 1. So here's another situation, okay? Suppose that in the past, we had a value of 130, and in the future, it's worth 234. So if I look at that change, what's 234 minus 130? Calculator. 234, where's takeaway? Help, I can't see it. Minus 130 is 104. So that's a change of 104. This is what we call an absolute change, not a percent change. To get the percent change, my R, I have to take the amount of change, the 104, and divide by the original amount, the 130. So this will give me the percent change. Okay? So this one right here is what we call absolute change. It's just a subtraction. And then this one right here is going to give me percent or relative change. So then we on the calculator, we whip out what is 104. Where's that calculator? Divided by 130, the original amount. And this tells me that my percent change is 80%, 0.8. Now that's just the percent change. To use it in a formula, I have to plug it into the growth multiplier thing, which says always do 1 plus R. Okay, so I plug that into 1 plus R, and I get 1.8. Okay. Now I just want to show you something really cool about future versus past. what if instead I took, and just forget about the subtraction I did to get the 104. What if I just took 234 divided by 130? Try that on your calculator right now. What does that equal? 234 divided by 130. Somebody speak it or chat it to me when you get it.
$1.8.
That is the 1.8, right? Isn't that cool? That's this number right here. The growth multiplier, it turns out, is always the new amount minus the old amount. Now, how many years or days go by in between, that kind of matters too, but here this is 1 year, let's say, or 1 month or 1 day. Okay, so that is the 1.8, same thing I have up here. So what this tells me in words is that 234 is 180% of 130. Another thing I can say is 234 is 80% more than 130. So there's a couple of ways I can use that information. With the 1, it's kind of a direct multiplier. Without the 1, I have to use more than. Okay, the 1 being the 100% difference in those two. Okay, so that's an important thing. So if I wanted to set up a model for this situation with the 130 jumping to 234 in the future, 234, then it would look something like A equals start at 130, the multiplier is the 1.8, and then raise it to the power t. All right, I think I have one more example for you before I set you free to work on this lesson together. Oops, back here, do I have one more example? We did the new car one. I guess that was my last example. Okay, cool, we're ready to jump in. So let's get out of the notes. We're gonna be working on lesson 1.2. There are 2 problems to work on. One is a car depreciation, starting at $26,000 and losing $15,000, 15% per year. And the other one is about Ebola outbreak in Africa, where they had 130 cases, and then the next month there were 234 cases. Okay, kind of like our COVID outbreak. The numbers with COVID are a little more extreme than the numbers with Ebola. COVID spreads easier than Ebola does, believe it or not. I think Ebola is scarier, but I'm not sure. Bleeding out is kind of scary with Ebola. All right, breakout groups. Let's stop the share. And